So this is an overview of our talk. We'll first see a brief introduction to the basics of Haskell, which will be covered by me. So Haskell, the name Haskell comes from the mathematician Haskell B. Curry, whose full name is Haskell Brooks Curry. And fun fact, he has three programming languages named after him, namely Haskell, Brooks, and Curry. Composition of functions is also called Kareem in his honor. Also, the symbol of Haskell comes from lambda calculus on which it is based. Even Lisp that we had seen earlier in the course is based on lambda calculus. It was introduced by Alonzo Church in 1930. So let's look at some features in Haskell. Haskell, the some of the prominent features of Haskell are that it is statically typed, which is to say that every expression in Haskell has a type which is determined at compile time. In fact, it is also sometimes known as typeful programming language. And all the type composed together by functions should like match up. Um, Another feature is that it's functional. So like Haskell, everything in Haskell is a function. Functional in the mathematical sense. We'll see a bit more on that later. Um, Another feature is that it supports type inference. So we do not have to explicitly write out or define that this function or this expression is of this type. It The compiler GHCI can infer it at the compile time. Uh, Shashwat sir will explore on that a bit further. It also lends itself very well to concurrency because um, in GHCI has a parallel garbage collector which helps in concurrent program computation. Also, it is lazily evaluated. So functions don't evaluate their arguments directly, but they map it out. And whenever it is required, only then will the computation take place. So let's see what the functional style is. So most of the programming languages we have seen so far, or I have seen so far, are imperative in style. Um, One second, I'm not sure what it is moving two slides. Yeah, so imperative in style. So initially, in the imperative style, what you have seen is like the simple program to compute it sum of numbers from 1 to n. There are two variables, total and count, which are initialized at the start of our program. And in each iteration, we continue to update their values. And so the count is increased by 1 and total is increased by the value of count. And at the end, we get the sum. But in functional style, we are mapping it. So it is much more similar to what we do in maths, like when we write it out in pure mathematical uh, usage. So when we have to calculate some sum, we do not write it so like 1 to n. What we do is we use summation I equal to 1 to n, and uh, using that we show the summation. Here we just use that, but in a bit more syntactical manner. So we have used sum and a list of numbers from 1 to n. So in imperative, stored values have to be changed, but in functional, functions are applied to arguments. Um, so let's see how functions are declared. So in order to clear any misunderstanding, a function is a mapping that takes one or more arguments and produces a result. As simple as that. And the syntax is like given. So square x is equals to x times x. But uh, this is the main line which is declaring the function. But there are some subtleties to understand. So first of all, functions here do not have any assignment operation. So Haskell does not have any assignment operation. Assignment as in there will be nothing like x times x is being assigned to x. So like the value of x will not become x times x. It is not that the input was x and the x is changed to x times x and that is returned. No. What is happening is we are mapping square x to x times x. So the evaluation of square x will evaluate to x times x. Another example of function is lower is also given. Now, another thing to notice, what is this notation, which seems like we are defining the type of the function, square, um, double colons, int maps to int. So the double colons is only notation used to show that whatever is on the left of double colons is a part of whatever is on the right of double colons. So like the mapping from all the integers to all the integers, square is a subpart of that. Similarly with is lower. This is how we define functions and their types. But we do not need to necessarily define it because Haskell has type inference. But it is very important when we are composing functions that the types need to match so that we do not have any problems. So let's explore currying. So in Haskell, functions can only ever take a single input, but still we are able to write functions such that they have two input arguments. So what happens is the if you have noticed that the add the type which we have declared is also add semicolon semicolon int mapping to int mapping to int, which is to say that add is a function which takes in as input a single integer and maps it to a mapping of integer to integer. So it returns a function. Here we have called it add x. So what add does is initially add x comma y. What does it do? So initially add will take as input x and return a function we are calling add x, and then add x will take the input y and return the value x plus y. And that is how currying takes place when we have a single function but multiple inputs. I'm pretty sure all of you must realize that when we have one function and we want to call, when we want to input it, pass as argument in it, uh, return value from another function. So we are not going to explore that much. So let's move on to types. So the basic types in Haskell are Boolean char string. So those of you who are sharp-minded must have got what's with the deal with int and integer. So int is int and integer is similar to float and double. So like int is fixed precision, and here in Haskell we have the advantage that integer has no limits. Like you can have an arbitrary long integer. Obviously, your system memory limits must apply, but in integer we have int we have 64 bits of precision. So 2 to the power 63 minus 1 to minus 2 to the power 63. Only those range of values will work. But in integer we have no caps on values. So let's see a bit more advanced data type. We have tuples and lists. In tuples, we have a collection of elements which can be same or different, it doesn't matter. And they are the arity of a tuple is the number of elements it has. We are not going to explore tuple much. It's not required here. So let's move on to lists. So lists are a collection of elements which must be of same type. We cannot have different types in the same list. Also, as we have seen in most languages, string is a list of characters in Haskell also. So let's explore a bit more about lists. So lists are constructed using cons operator. This is quite similar to what we have seen in list. It's just that the syntax is a bit different. So list of elements 1, 2, 3 translate to a list of 1 cons, 2 cons, 3 cons, empty list. There's also this concept of infinities in Haskell. So in Haskell, we can say that we have a list with infinite number of ones. That isn't to say that it will take an infinite memory and actually store all the ones. It is a form of expression. So here, what we have defined is like, it is a recursive kind of definition if you see. So ones is equals to one semicolon ones. So um, the expression will be used. It's not that the entire infinite list of ones will be used. This is a very powerful thing that Haskell has. So, if you would like to explore further, we have some books at the end of our slides, and there's a very nice talk on Google Tech as in Technology Talks, and Amal Deswar is also very proficient in Haskell. So I'll call upon Nadish to explain what is parametric polymorphism next.
Hello. Change this line. So good morning to everyone. Here, polymorphism in a general mode. Polymorph. Hello. I'm audible. Hello.
Yes, you are audible.
Okay.
Yes, you are audible.
Okay. Polymorphism having multiple forms refer to construct that can take on different types as which we need it. And there are also three forms of polymorphism. One is parametric polymorphism, ad hoc polymorphism, and subtype polymorphism. As which we discuss, polymorphism is a way to define types or next slide, please. Parametric polymorphism is a way to define types or functions that are generic over other types, and which is using parametric polymorphism. A function or a data type can be written generically so that it can handle values uniformly and without depending on any other types of polymorphism. And here, for example, and we can see that some examples like a function append that joins two lists can be constructed so that it does not care about the type of elements. The examples of append in two integer list and append two char list, and these are two examples. Polymorphism in Haskell will be explained by Saina ma'am.
Yeah, hello. Okay, parametric polymorphism in Haskell. So as Nadesh already told, like parametric polymorphism is where you are able to write functions or declare data type generically without depending on their types. So in Haskell, we actually use type expressions, basically expression which is containing type variables to denote the types of such polymorphic generic functions. This concept of type variables will be clear in the coming slides. So mainly, I will be looking into how to write polymorphic function and how to declare polymorphic data type in these slides. Okay. So first of all, let's look at polymorphic function. So what is a polymorphic function? It's a function that works for many different types. For instance, take the example of the length function. Okay, so length is a function which takes a list as its argument and gives the number of elements in the list. So this length function need not depend on what type of list you give as an argument, right? So length is a polymorphic function. For example, if here the length is applied on a Boolean list containing three elements, it returns a value integer value 3. Similarly, length is applied to an integer list containing values 1, 3, 5, 7. It gives an integer value 4. So here the length is a polymorphic function. Now how we will denote the type of this length function is as Pulak already. So here we always write function and this operator, and this is the type of the function. Okay, so the type of the length function is it takes a list of any type and returns an integer value. So the list of any type. So here we used a type variable to denoting the list of any type. So here A denotes the type variable. And what is type variable? As the name suggests, a type variable is nothing where a type variable is like where you can actually use for denoting any type. For example, A is a type variable. It can take hold of int or string or boolean or anything. So length is a function which takes a list of any type A and it returns an integer value. Now let's see how can we define this length function in Haskell. Here we have used two concepts. One is pattern matching and another is recursive functions. And we have already seen the concept of pattern matching in Prolog, as well as we have seen the concept of recursive function in Lisp. So both pattern matching and recursive function is supported in Haskell. So here the length function works like, okay, first of all, the length, if the length is applied to an empty list, length is 0. Length applied to non-empty list. So as Pullak already told, so every list can be constructed using every list is constructed using cons operator. So I can represent the list as the head of the element cons the remaining part of the list. So I have put, so here wildcard character is used because I don't care what is the first element of this length, first element of the list. So length of this non-empty list is equal to 1 plus the length of the remaining part of the list is x. Okay, so the main point to note here is that a is a type variable, which means the length can be applied to list of any type. And usually the type variables are denoted using small letter a, b, the words which starts with small letter. Let's see some more examples of polymorphic functions. Now head is another example of a polymorphic function, and what head does is that head given a list of any type gives the first element of the list. So here head is again a polymorphic function. It does not, we does not need to depend on the type of the list to give the first element of the list. So how we'll write the denote the type of the head function. So the type of the head function is it takes a list of any type a list of type A, and then returns the first element in that list. So that will be same as A. Okay, this A should match with this A. So how we'll define this head function is head is applied to non-empty list. So a list which is where x is the first element, cons x is the remaining part of the list, and head of this list is same as x. Now you can see that head is applied to an integer list to give the integer value 1. Now head is applied to a character list, character A, character B, character C, character D, to get the first element, character A. Now let's see another example, swap. So swap is a function which takes a tuple of two elements and returns again a tuple, but the two elements being swapped. So here, what is the type of the first? We will see the type of the swap function. So it takes a tuple of two elements. So as Pullak already told, tuple is like a sequence of different elements, different types, elements of different types or same types, doesn't care. So we take the swap function takes a tuple of two elements where the first element is having a type A and the second element is having a type B. And here A and B both denote type variables, and A and B are independent. Like they does not depend, like they can be of the same type, they can be of different type, doesn't matter. So swap function takes a tuple of two elements, of first element being of the type A, second element being of the type B. It swaps a value of tuple of elements, where the first element now becomes of type B, and the second element will be of type A. So swap tuple xy is same as y comma x. So here you can say when I swap a tuple of first is an integer value and the character value, I'll get a tuple of character and integer. So here, what we have seen is the set of types associated with a function is actually given by a type expression that contains type variables. So even if you see here, it's a type expression, like it contains the expression which contains type variables, type expression. So the we denote the types of the polymorphic function using type expressions. Now, let's see some polymorphism in higher order function. So we are already familiar with this concept of the higher order function in Lisp. So what is higher order function? Higher order function is the one that takes function as an argument or returns a function as a result. So we are already familiar with the map function also in Lisp. So map function takes a function and a list and applies a function to each element of the list. So this is an example. So I am mapping function even to a list of integers. Now what is function even is? Even is like it takes an integer value and checks if the integer value is an even or not and returns a boolean value accordingly. So what is the type of the even function? It's int arrow bool, and this is integer list. So I am applying this even function to each of this integer value to get a boolean value. So after applying, I'll get a list of results after applying this function to each of the elements. So how we will denote the type of the map function in Haskell. So type of the map function, first of all, it takes a function and it takes a list to give back a list. So the function, it takes a generic function. So the function has an input of type A and output of type B. Now this function is to be applied to a list. So it takes a list of type A. And then after applying, it will give the return value will be of type B. So it gives returns a list of type B. Okay. Uh, so map fxs. So how we will define this map function in Haskell is we'll use a list comprehension notation, which is same as the set comprehension notation we have seen in Max. That is, I am about to map this function f on the list xs will be equal to a list of values where each value is obtained by applying this function f on a x where x is drawn from the list xs. Okay. Now let's see one more example in higher order function, which is filter. So filter, this is also we are familiar in the list. So filter takes a predicate and a list and returns a list of elements that satisfy the predicate. Similarly, we are applying filter even from the this denotes list of numbers from 1 to 10. So filter even from 1 to 10. So you will get all those even numbers from 1 to 10. So here, what does a filter does is that it takes a predicate. So always a predicate takes an argument of any type, a particular type, and then it gives a returns a Boolean value. So here filter takes a function whose input is of type A and output is of type bool, and then it also takes a list of type A, and then it returns a list of type A. I mean those elements which satisfy the predicate. So filter P xs is equal to, again the list comprehension notation, set of all x such that x is drawn from the list xs and p when applied to x is true. Okay. Now let's see bounded parametric polymorphism. What if so in parametric polymorphism a function may have infinitely many types because you're using the type variable a and type variables, and type variables can be that can take any types, so there can be infinitely many types. What if you want to restrict the types to certain subset of types? For example, consider we need to write an add function. That is, I want to just add two numeric values. Okay, it can be two integer values, it can be two float, it can be two double values, and so on. So what, ignore this part for now. So what we have right now is a polymorphic type variable. So okay, to denote the function add, we will use this type variable. Okay, the add function will take two arguments of type A and will return the result of type A itself. Again, so what if I wanted to restrict this type to numeric values? There we use the concept of type classes. And what is type class? It's a set of types which support certain collection of functions defined by the class. Here, num is a type class that contains types whose values are numeric. This int, integer, float, double all comes under this num type class. So num has certain functions. So these are the functions which is defined by the num class. So all those types which comes under this num class should actually support these functions. Okay, and how we will restrict this is, okay, here the add function, it tells you, okay, to take two arguments of type A and return the result of type A, provided that type A is under the num class, num type class. I.e., the type A should be supporting these all functions. There are other built-in types like equality, ordered, and all. Equality is like equality type class has functions like equal to, and not equal to, and all those types which supports these functions will come under this equality class. Similarly, there are other type class like ordered, which has functions like less than, greater than, etc. So all those types which support this function will come under this ordered class. So these are some of the built-in type classes. Now we can define our own type classes as well. We can define our own type classes, and we can define our own functions, and we can have different implementations for the same function for different types. But this concept comes under ad hoc polymorphism, which is another term for overloading. That is, the same function has different implementation for different types. So when Garrett explains the comparison using examples, he will give one example of ad hoc polymorphism. There you will see these things more. Yeah, now we will see. So till now we were seeing how to write a polymorphic function and how to denote the types of the polymorphic functions using type variables, i.e. type expressions. Now we will see how we can declare a polymorphic data type. Before declaring polymorphic data type, we will see how we can normally declare a new data type. we already know bool is a data type. So bool has values like true or false, right? Similarly, suppose I want to declare a node type, say OS, and I wanted to have values like Windows, Linux, Unix in the OS type. So I'll use a data keyword. So this data keyword is used for declaring node type by specifying their values. So it will be like data OS equal to it can take values like Windows or Linux or Unix. So this is how we normally declare node types in Haskell by specifying their values. Now, let's try to define a data type for trees of different types. So trees can be of trees of integer or probably trees of strings or trees of bool, etc. So how we can polymorphically declare the data type for trees? So again, we will use this type variable. So here I'm using the data keyword and then tree a. A denotes tree of any types can be equal to a tree can be either a leaf node with value of type A, or it can be internal node with value of type A. So this is a binary tree, and it has a left subtree is again of type tree A, and its right subtree is again of type tree A. For example, this is a tree of integers, and this tree of integers is denoted using this expression. If we declare the tree as this. So here node 1 and its left subtree is a leaf dot leaf 2, and its right subtree is again a node 3 with its left subtree as leaf 4 and its right subtree as leaf 5. So the type of this expression is tree int, because a here is integer, it takes the value of integer. Yeah. So now I'll hand over to Sakar for explaining templates in C++.
From this slide, we will discuss about the parametric polymorphism in C++. So the templates in C++. So the templates are the powerful feature of C++, which allows you to write the generic programs. So the idea is simple, that is to pass the data type as a parameter so that we don't need to write the same code for the different data types. So the templates are often used for the purpose of code reusability. For example, a software company may need to write the sort function like a bubble sort, quick sort for different data types. So one approach will be like write the different code write the different code for the different data types. So rather than writing and maintaining the multiple codes, we can write one sort function and pass the data type as a parameter. So the concept of the templates can be used in the two different ways. So first is a function templates and other is a class templates. So the first we will look at the function templates. Next slide. Yeah. So the function templates work very similar to the normal functions with the very little difference. So the main difference between the normal function and the function template is that a single function template can work with the different data types at once, but a normal function can work with only one set of data types. So how to declare the function template? So the function template starts with this keyword template, which is followed by the template parameter inside that greater than less than sign, which is comparison operator. Then comes the function declaration. So in the given declaration, capital T is the template argument that accepts the different data type like integer, float, any both. So when an argument of data type is passed to the sum function, the compiler generates the new version of sum function for the given data type. So these things will be more clear. So let's see the function template examples in the upcoming slide. So yeah, so in the given slide, the function template mymax is defined that accepts the two arguments x and y of type t. So the mymax function simply returns the largest among the two arguments using the simple conditional operation. So coming to the main function, so main function calls this mymax, which will work on the integers 3 and 7. So the compiler internally generates the code like which is shown in the top right corner. So yeah, the t will get replaced by the data type int in the inside. So it will be like int mymax, and arguments will be like int x and int y, and the rest function will be like whether x is greater than y or not. This will be performed. So the same thing happens for the character also. So compiler internally generates the code like char max, char x, and char y, and the rest is same. So now you must be thinking that can we pass the template parameter with the different data types? So the answer is yes. So let's see the other example in the next slide. So yeah, so here we have passed the two templates that can be of different data types. So here are equal function that accept the two arguments. One is A of type T and other is B of type U. So function is checking whether these two arguments are equal or not. So the coming to the main function. So you can see here R equal function is getting called where int and double are the template parameters. So we have passed the 10 as an integer and 10.0 as a float to the R equal function. So then it will perform the rest operation whether they are equal or not. So the here internally the compiler will generate the code like bool are equal and in the arguments like int a and float b, and it will perform the rest operation like whether they are equal or not. So the this program will output answer like yes, x and y are equal. So the next slide. So yes, in the next slide we will discuss the class templates. So here, like function templates, you can also create the class template for the generic class operation. The idea is simple. That is the pass data type as a parameter, so that we don't need to write the same class code for the different data types. That is, you might need a class implementation that is the same for all classes, only the data types used are different. So the normally you would need to create a different class for each data type, but this will unnecessarily increase your code base and will be hard to maintain. So how to so they have introduced the concept of the class template. So how to create the class template? So like function template, again it starts with the template keyword. In the given declaration, capital T is a template argument, which is then followed by the class declaration. In the class body, member variable var and member function are both of type T. So this thing will be more clear with the help of examples in the upcoming slide. So yeah, uh, in the given code, there are two different template parameters that can be of different data types. So thus we have in the class test, uh, we have declared class test which has member variable a and b of type t1 and t2 respectively. Then it have the test function with x and y as argument of type t1 and t2 respectively. So here the x and y are just getting stored to a and b, and the show function is just simply displaying those a and b. So the program is very simple, but the idea is to show how we can use the class template with the different data types as a template parameters. So the coming to the main function, here we have created the object of the class, just like how we create the object of the class, like class name and then object name. So in the same way, there is little difference. We have created the template object as shown in the code. So we just have to add data type in between the class name and object name, and the rest is same. So here you can see the same class code is used for the two different object having the different data types as arguments. So yeah, this is all about the class template and function template. The next slide, from the next slide, Jared will cover the rest.
So now we have seen how polymorphism happens in C++ and Haskell. Now what we are going to do is we are going to take an example, and then we are going to see what are the different implementations you can have in Haskell and in C++. For our example, we'll take addition. Here in this example, addition would mean 1 plus 1 equal to 2 and 1 plus 1 is equal to 11, which means it could be a numeric addition, mathematical addition, or it could be a concatenation or append operation. So if you look at this example here, so this is which is in blue, that is like it's a sectioning example wherein we try to overload the operate a mathematical operator. Okay, so this we could overload this the plus a plus plus operator, which is append operation in Haskell, or it could be we could replace this with a plus, which could be a addition operation. Now I have just created a new operator here, plus plus minus. So what it says is it takes um, uh, on the right, the last three A's that is there, it takes what Sanya has already explained, occurring operation, and it takes a value and then generates a function that gives another function. Now this is an example of a bounded parametric polymorphism, which is already explained. Now, what happens is we are considering only the values here that are of numeric. Now, if you look at once, so then what you do is in the next line, I'm just using this operation in between I'm creating this operator and then using. Uh, Sanya, can you go back? Um, Okay, yeah. So I'm just replacing this operator with a plus operator, a mathematical addition operator. So at the GHA command prompt, when I use this operator, it 5 plus 10 gives me 15. Similarly, in the second example, in the first case it was a int value. In the second case, it's a there's a decimal point, right? It's a fractional value. So it does the operation in this case. In third case, we have two values, one of int type and one of a fractional type, and then both of these you are able to do addition because they both of these are type numeric. Next slide, Sanya. Okay. In this case, what we will do is we'll try to overload we'll create another operator to join the two lists in Haskell. So we have the section here, plus minus plus operator that we have created here, and then just that replaces this new operator with the plus plus operator. The plus plus operator used to append to lists. So if you look at the example here, ABC plus minus plus CDE, it appends the value. Similarly, in the second case, we have a list. In both of these cases, in Haskell, they are a list because there is no string in Haskell. It is a character array that is there. So both of the second and the first are the same. In the third example, it's a list of numbers, and we append both of this. Now, remember that both of this will need to be the same type because on top we have said A. If we had another type, we'll need to say B. So on both the sides of the operator, they will need to be of the same type. Next slide, Sanya. Okay. Now, Sanya mentioned about something called as ad hoc polymorphism. So this is a case wherein you try to overload um, something but give it a different implementation. Now, in the previous two cases, we have seen that it was doing the same. The behavior was same. In the first example of parametric polymorphism, it was a numeric mathematical addition, and in the second case, it was append operation. But here, depending on the type that you get, you should be able to give it some implementation. Now, don't worry much about the syntax here, but just remember in Haskell, you can do something called as classes here. Now, this class, so I'm creating another operator plus plus plus, and in the class, I'm just giving the definition, or the type definition. And then what I do is, just like in any object-oriented language, you can create instance of a class. In Haskell, you need to create instance of this type class. Like for example, I have this type class add that has the operator plus 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 and takes from um, takes two values and then gives you a third value, a curried value. Uh, what I've done is I've created the instance of this type class add named integer, and if it is an integer, then what I'm doing is I'm doing a mathematical addition. Similarly, a second instance I've created, if it is of type string, then I am doing a append operation. So if you see on the right, in the first two cases, they both of them are lists. because there's a double quote there, a list of an array and a list of characters, and both of them append the values. In the third case, however, both of them are numbers on either side of the operator, and it gives me a arithmetic operation. Next slide, please. Okay, so now before this concept of generics and templates in C++, we did have object-oriented concept in C++. So, and the way you could achieve this was through use of overloading, which is uh, which is one of the four main concepts that makes up a object-oriented language. So what we'll do in this example is we'll take a plus operator and we'll overload it for our example. So what I have done here is I've created a class called number, and this number has an attribute called value. Now this value is of type int. Okay, so and then it has some functions and constructor here. So let's come to the third function kind of thing that is in the class, that is numeric number operator plus. So here what I'm doing is I'm overloading the plus operator for this class. So ideally you cannot add two objects by themselves, right? You can add two numbers, you can add two floats, uh, because they or you can because there i- that operator is defined for the data type, but this is your own class. How do you add two class? How do you add two class or two objects of a class? So you need to create your own you need to overload the exist an operator for this class. So in this case what I'm doing is I'm saying operator plus, I'm trying to overload this plus operator, and then for this object I'm taking a pair in the parameter list, I'm taking um, another object reference, a constant object reference, because I don't need to change the value in that one. And then I'm in the method definition here. What I'm doing is I'm creating another object here, and then I'm adding the individual values, individual data that is there in value attribute, and I'm returning this object. So if we go to the main method, a and b is two objects. I'm adding and num c equals a plus b. So ideally this shouldn't be possible now because we have overloaded the operator. We are able to do that. So c, once you do c out get value, you will get the value 30, that is 10 plus 20. In then what I'm doing is number d and e, both of them are floats. Okay, uh, but C++ it typecast it to an int value, so it will just drop the decimal and anything after that, because the value here in the class number is int, and here also you will get the value as 30. Next slide, please. Okay, so we have already seen, Sagar has already shown what how to create function template. So here what I've done is I've just created a template to add, and here and in the angular bracket I've mentioned the type name T. Now these are, it's very it's not that you need to always say T. You can say any alphabet name, but generally as a standard they follow from T, U, V, and all. Okay. Uh, so as a standard they are putting T. Okay. So now once I say template, and then in the angular bracket I say type name T, which means any type, and then in this function next line it is t add. So the t is what is returned, that means you return a value of this type t, and then in the parameters you take two uh, variables of type t. So for example, if t is integer, the it will return an integer and it will take two integers as on the parameters. If you go to the main function here, int uh, sum I underscore I, so you say add, and then I have typecasted it here to int, and then 10 and 20. Okay, 10 and 20, and it will give me it will call this add method, and since both of them are integer, it will return me an int. Similarly, in the second case, float sum underscore f, here what I've done is, I've taken two values in the parameters when I'm calling this function, and I've typecasted it to float. And in the third case, we have two strings. um, so string is, I had to call a string library class, and then string hello by, and then it has um, concatenated this string. Okay, next slide please. Okay, um, so um, so this example is pretty similar to what was there just now, what we have seen. The only difference is, if you see here, is in the Angular bracket, instead of type name, it is class. Okay. So, so this is a very basic example. Uh, which is why, so in most cases, type you can, in for a type, you can either say type name or class, and many times they are used interchangeably. And then there are many definitions of C++ and many editions of C++. So when you're trying to create any templates, so make sure that you check which version of C++ and which edition of C++ you're running, and check whether, if you want to use class, whether it supports the uh, types that are primitive, or whether it only supports real classes. So in this edition, so I was using this in GCC compiler uh, on Ubuntu, and in this case it worked. uh, so on the right, in the in the main method, when I'm saying 10 and 20, it worked because it considered that as a type. But certain compilers, you need to check whether it supports the class accepts primitive data types, or only it expects real classes that is there, object oriented classes. Okay, next slide please. Okay, so now we look at an example wherein we are going to create a class template, but in the object oriented style. So we have a template, a type name t. Here you can put either type name t or class t. I just explained, right? Because depending on the compiler, but just to be safe, I've put type name t, and then I've created a class item. Now this item has an attribute called value. Um, so what I've done is, I said I then for this class item, I'm overloading the plus operator. And similar, just like how we have seen the uh, operator overloading example, I'm using this class to take in any value, and then um, uh, do addition on that, um, addition or a concatenation on this value. So if you see here in the main function, um, we have, in the first example item int1 int2, I'm taking two integers, um, I'm adding them, and then I get the int value. So in this case, what will be printed out is 30, that is 10 plus 20. In the second case, I'm taking float value, I'm typecasting it to a float, in that, so this class item, for this object float1 and float2 will expect a float value. So I'm saying 10.3 and 20.8, both of this, when I'm calling this plus operator, sum float equals float1 plus float2, it, and then I'm uh, printing it out onto the console, it will give me 31.1. And in the third case, I'm taking a string. Okay, so item string 1 string 2, so object string 1 and object string 2 of class item, they will take the value as hello and by respectively, both of these will be strings. And once I'm doing a plus, I'm doing a plus string one st1 str1 plus str2, it will concatenate both of these options, and this will print out uh, hyphen hello hyphen hyphen by hyphen. Yeah. So this was about the different implementations of polymorphism. Now I hand it over to Saswat.
Uh, Next slide, please. Yeah. So basically, we have seen a syntactic difference between Haskell and C++ when implementing the parametric polymorphism and other polymorphism. So now we let's discuss about how generally they have implemented in both the language. So there are basically two ways of implementing a parametric polymorphism. One is implicit, another is explicit. Implicit one is straightforward. The user do not have to give any specific data type in source code itself. So this kind of the implicit parametric polymorphism is implemented by Haskell. Whereas in case of explicit, user have to give different data type for different instantiation of polymorphic functions. So C++ implements that kind of polymorphism. So let's now dig deep into the how the both the language implements this polymorphism. Let's take a case about Haskell. Next slide, please. So before looking at how Haskell implements the polymorphism, let's briefly know about discuss about type systems in Haskell. So we are not going to discuss about in a lot more detail, but there are basically three interesting aspects to types in Haskell. They are strong, they are static, they can be automatically inferred. So when we say that Haskell has a strong type system, we mean that the type system guarantees that program cannot contain certain kind of errors. These errors come from trying to write expression that do not make sense, such as using let's say taking an example for plus operator. Plus operator expects a numerical value as argument. When we give when given a string, it prompts error because it expects a numerical value. That's why we call it's a strong type. Second is static type. Having a static type system means that the compiler knows the type of every value and expression at compile time before any code is executed. A Haskell compiler will detect when we try to use expression whose type do not match, and reject our code with an error message before we run it. Here is an example is true and false, but the false is in a it's a string, not a boolean value. So so uh, when uh, when we evaluate this expression, it gives an error at compile time. So Haskell compiler will detect we try to use an expression whose type do not match, and it's reject our code with error that could not match expected type, a bool against inferred type character string or character array. So so Haskell's combination of strong and static type makes it impossible for type errors to occur at runtime. While what this means is that we need to do a little more thinking upfront. It is also eliminates many simple errors that can be otherwise be very hard to find. So it is a cliche within the Haskell community that once code compiles, it is more likely to work correctly than in other language. So perhaps a more realistic way of putting it this is that a Haskell code often has a few trivial bugs. Third aspect is type inference. So a Haskell compiler can automatically deduce the type of all expression in a program. This process is known as type inference. So Haskell allows us to explicitly declare the type of any value, but the presence of type inference means that uh, this is almost always optional, not something we are required to do. So these are the interesting aspects of the type system. Now we can dig deep into how Haskell compiler handles polymorphism. Next slide, please. So, as we already know that Haskell polymorphism is called implicit polymorphism because programs that declare and use polymorphic function do not need to contain types. So, a compiler has no way to find out what the real type is or to manipulate a value of that type. So, it cannot create a value, neither it can inspect one. So, all it can do is treat it as a fully abstract black box. So basically it doesn't care about the type. So there is a deep mathematical sense in which Haskell does implement the polymorphism. The one paper named Theorem of for Free by Philip Wadler covers this procedure in depth, but we don't have to go in detail in that. The paper discusses more on logic side of polymorphic functions. So the type inference algorithm, before we already seen that type inference algorithm computes when a function is polymorphic and computes the instantiation of type variables as needed at compile time. So basically this is the way Haskell compiler handles the polymorphism. Next we will see C++ compiler, how C++ compiler handles polymorphism. Yeah, so we already know Haskell implements implicit polymorphic function. So C++ implements the explicit parametric polymorphism where the programmer or user uh, have to give a data type beforehand. The program text contains data variables that determines the way that the function or the other value may be treated polymorphically. So explicit polymorphism, that's why explicit polymorphism often involves an explicit instantiation. Template code will be expanded at the compile time. Multiple version of that code created at compile time by using type checking. Before that type checking will happen, how many different types have been passed to a template. According to that, different version of code will be created at compile time. While compiling source code line by line, if compare stumble upon a template, user pass different kind of data type to call a polymorphic function, then different separate version of the same polymorphic function and class got created. Then the code size will increase and each version will be mapped to its callee function by at the linking stage. So this is how C++ handles the explicit parametric polymorphism. Now let's compare both overall comparison between Haskell and C++ polymorphism. So C++ templates and Haskell polymorphic function are implemented differently. The reason for the difference is not related to the difference between explicit polymorphic syntax or implicit polymorphic syntax. The need for different implementation technique arises from the difference between data representation of C++ and Haskell. We don't need to go deep into that, but so as I said earlier is that C++ templates are instantiated at link time. So basically the two important point of comparison is efficiency and reporting error messages. As far as efficiency is concerned, the C++ implementation requires more effort at link time because um, and the produces a large code size because the instantiating a template several times will result in several copies of code. So Haskell implementation, so that's why it takes more time at the linking stage. Whereas the Haskell implementation will run more slowly unless a special optimization are applied in a type inference algorithm. So type inference algorithm plays very important role here. More the efficient algorithm it is, the less overhead it is. So another comparison fact is reporting of error messages. One reason is that separate in case of C++, the separate program modules are compiled independently, but are linked together when only the entire system is assembled. So link time error represents a global, so basically we get a very link time error. So in C++ link time error associated with the operations in templates that can be very irritating and a source of frustration also, because when we run, if there are a lot more error, we cannot easily identify the error, whereas Haskell prompts any error at compile time, which is way more easier to handle. So as a general programming principle, it is more convenient to have a program errors reported at compile time than at link time. These are the basic differences in their implementation in both Haskell and C++. So though there are very different implementation, but they have been using in different use cases also. So we need to find out which suited for our use cases. So these are the overall comparison between Haskell and C++. These are the reference. We have given some books to refer. Yeah, thank you. Yeah, any questions?
No questions.
I just had a small doubt. In the comparison using examples, I didn't understand how that was defined. Plus minus plus function that was joining two strings or
Jared, can you explain?
Yes. Can you move to that slide?
yeah, this one. How is it? How is it adding? Like how I didn't understand how we defined it. This AAA.
Um, okay, so like Sanya explained um, the this no what is that currying function wherein you take so basically in this case we will be uh, taking each of the parameter one at a time, but we are taking two parameters and then we take first the first
Yeah, Jared, 1 second. Uh, these two lines, it's Siddha. These two lines, the first line is telling what is the type of that operator. The second line is giving the definition. Okay, so what is the type of this plus minus plus operator? It takes a list and another list and gives me back a third list. Yeah, the first list is the first parameter, second list is the second parameter, and third list is the output. Okay, so that is what this operator's type is.
Oh, but sir, how does it then imply? Sir, it's all arrows, so it's all looking the same. So how does it then infer that these first two A's are input and the third is output?
No, I mean, if you have n arrows, it means that it takes n minus 1 arguments and the last one is the output.
Okay, sir.
Okay, so so it will take one by one, just like in C program. If the C program has n arguments and return some value, then its type will be x1 arrow, x2 arrow up to xn arrow y. Okay, so x1 will be the first argument, x2 will be the second argument, and so on. Xn will be the final argument, and y will be the output. Okay, so any function which takes n arguments and returns a value, and Haskell will always return a value. Okay, there are no void functions in Haskell.
Oh, okay, sir. That clears it for me.
Okay, and the second line is just saying what is the definition of this plus minus plus. So it says x plus minus plus y is same as x plus plus y. That's all. Okay, so plus plus is already defined as an operator.
Okay, sir.
All right. Okay, any other questions? I really like the presentation. They covered a lot of things. Yeah, so you see that, I mean, whatever you do in Haskell with for types and this thing can be done using templates in C++. Yeah, though there is a issue of efficiency, because C++ at the end before compiling will create copies for each data type. That's what they call explicit parametric polymorphism. But in Haskell is a lazily evaluated thing. So nothing will be created till you need to run it. All right, very nice presentation. Thanks a lot.
Thank you,
And
sir.
yeah,
Thank you, sir.
yeah. So now we have two more left. Yeah, one is Siddharth's and the other is the last group, 7th group, and then
Sir, I think Rajora's group is also left. Uh,
okay. Anyway, so this week I'm a little busy, but we'll find some time. When is the classes ending?
sir, we have end sem, like first end sem for us third years is on Tuesday. So after that, it's all one after the other.
Okay. So before, yeah, then you will present tomorrow morning. Yeah.
Yes, sir.
Okay, and all right. So tonight at 8 o'clock there will be a presentation. Yeah.
Yes, sir.
All right. Yeah.
Sir, just one more. In the ancient timetable, our exam is listed on 20th. So you will be. I just wanted to confirm that that is the final date for us.
Yeah. So if it is on 20th, we'll keep it on 20th. It will be C++.
Okay, sir.
Okay. It will be
Mhm.
this thing will be C++. Whatever we have learned in C++. Okay.
Okay.
Maybe I'll ask you to write a program or something like that. So. All right then. Let's meet at 8 o'clock. Thank you.
Thank you, sir.